So here we go. Scales and proportions. As always, throw your name on the front here. You guys are block A. This is my book. So that when I find your book, I can return it to you. Here we go. So this is a little different than the stuff that we've been doing. I think it's a nice kind of, I think it's a relatively easy way to end out the semester. Whichever one you want. Sure. It's going to use a bunch of fractions, but other than and equivalent fractions, but other than that, that's it. So here we go. So scale models or diagrams. So a model or a drawing. If you're in a model building, you'll have seen this stuff before. But a model or a drawing in which the measurements are proportionally enlarged or reduced from actual measures. And what we mean by proportionally, you have a scale model or a scale diagram of something if all of the measurements are shrunken or enlarged by the same amount. Okay, so proportionally, if something is proportionally enlarged or reduced, okay, gentlemen, are we good? Okay, means all measures are enlarged or shrunk by the same amount. So the most common use of this stuff is to show a miniature version of what large, it doesn't have to necessarily just be a building, but miniature versions of what larger things look like. So if you're into like building model cars or model planes, boats, trains, all that kind of stuff, right beside you in that box right there. You're going for the scales and proportions one, yeah. They're designed to show you what a smaller version of that large object would be like. So a common example is this guy here. So this is it's hard to tell the difference when they're not colored, but this is an actual picture of a condo building on Ware Street. It's the one with the yellow balconies and yellow walls. And then this is the scale model of that same condo. When these guys were planning out, or when the developer was planning out what the property would look like, they build scale models of things. They put the buildings down, they put the scale cars down, the scale people down, and then they make the tweaks they need to make so that when they actually build the thing full size, they've got an idea what the stuff's going to look like. So if the scale models or diagrams are smaller than the original or real size, we call this a reduction, which I think makes a lot of sense. And if the scale or diagrams are larger than the original, we call this an enlargement. So enlargements often happen in science because lots of the stuff that you guys have looked at in your, or if you have science next semester, a lot of the stuff that you guys are going to look at is going to be much smaller in real life than is useful to study. Things like cells. That is an animal cell. They are not this big, obviously, because you would see them growing out of you. You'd be all bumpy and bulbousy. Because these are the kind of cells, this is the shape of a cell that makes up you. We have plant cells, we have animal cells, you have animal cells, obviously you're not a plant. And then DNA. We've got tons of this stuff coiled up inside every single one of these cells, so to draw it out like this, or sometimes you'll make models of it in science class, depending on who your science teacher is. You'll make models of this stuff. Obviously, that's an enlargement. And does anyone know who this is? Yes, who said that? Fantastic. Yeah, Derek Zoolander. If you've not seen the movie Zoolander, it's a wild ride. It's right up there with Dodgeball. He's a male model who can only turn one way. It's weird. And if you've seen the movie, you get the reference. If you don't, no amount of explaining is going to make it okay. So flip the page. So we've got a few ways to represent scales. So how much a scale diagram is described. So sorry, this is incorrect. This is not meant. This is messed up. Get rid of this. A scale diagram can be described by a scale factor. And we can write the scale factor a couple of different ways. One way we can write the scale factor is by demonstrating it as a fraction. So the scale factor is how the object has been either multiplied bigger or multiplied to get smaller. So this scale factor here is just a multiplier. Multiplier. To either blow up or shrink whatever it is you're looking at. And to calculate the scale factor, you take the A length in your scale diagram. This is the new drawing or the new model. And you divide it by the equivalent length in the original. And the original is the real thing, whatever that happens to be. And doing this division, or setting it up as a fraction, and then reducing that fraction, will tell you what the scale factor is. What do I have to multiply the original by to get our scale diagram? So a scale factor of 1 means that the diagram and the original are the same. Whatever the measurements are, if they're equal, something divided by itself is 1. So a scale factor of 1 means that your object is the same. If I drew you, I laid you on the ground and we traced you out, and we were able to like perfectly match, all your eyes were the exact same shape in the drawing, your nose, your ear, all the bits and pieces of you. We drew you out on the floor. That scale diagram would be the same as you. The scale factor would be 1. A scale factor between 0 and 1 means that the numerator here, the scale diagram, is smaller than the original. So that means what you've got is a reduction. So here we've got an original, and we shrunk it. And maybe that's a drawing, maybe it's a toy, I don't know. And a scale factor that is bigger than 1, if this number is larger than 1, that means you have an improper fraction. You've got a numerator that's bigger than the denominator. And what that means is the scale diagram, or the measurements in that scale diagram, are bigger than the original. And what that means is you've enlarged this thing. Scale diagram is bigger than the original. So maybe your original is, I don't know, Hot Wheels. You've got your little toy die-cast metal car, and you blow it up. Not literally, but you make it bigger. You made this thing bigger. So if I've got a scale factor of 2, is the diagram bigger or smaller than the original? It's an enlargement. And so specifically, it's an enlargement how much? Yeah. A scale factor of 2 means this thing is twice as big. So your diagram is twice as big as the original object would be. A scale factor of 1 over 2, well, if 2 is bigger, then a half is going to be smaller. It's a reduction. And specifically, that reduction is half as big. So then this one's going to be enlarged. This one's going to be smaller or reduced. I'll use R for reduction. 2/5 is going to be, it's going to be a reduction. And then 3/2, this, I mean, and you can think about these things as, instead of leaving them as fractions, lots of you guys like to convert these things to decimals. 2/5 is what as a decimal? Sorry? Yeah, 0.4. And 3/2 is what as a decimal? Maybe it helps to go to mixed number and then to a decimal. 3/2, how many times does 2 go into 3? Once, with 1 left over. That's going to be 1.5, which is 1.5. So what if our scale factor is 1.5, is the diagram bigger or smaller? It's bigger, it's an enlargement. The diagram is 1.5 times the original. So, let's draw some stuff. It's like graphing, but there's no axes. So if I want to draw this image using a scale factor of 0.5 or a half, is this thing going to be bigger or smaller? It's going to be smaller. This is what we want to do. If this is our original, and we want a scale factor of a half, we're going to end up reducing this thing. And in order to draw or make or build a scale enlargement or reduction, what you need to do is you need to multiply each measurement by the scale factor. So if we're going to redraw this thing, make it half as big, let's start with, I don't care what side we'd start with. Someone pick a side to start with in this object here. The top side, okay. So this top side is 2 units long. So if this guy here is 2 units, and I want to scale it to be half as big, 2 times 0.5 is what? Or what's half of 2? 1. So then if I'm going to redraw this side, I need to make it 1 long. Doesn't matter where on the graph or where on the diagram I put it. I just need to make sure it's far enough away from the original so that they don't overlap. So there's this, then that little green line there is the new top. And so now what I'm going to do is I'm just going to go around the object. Doesn't matter if you go clockwise or counterclockwise, but I'm going to go around the object, and I'm going to do the same thing with each side. So I'm going to go clockwise here. This side length 2 became 1. This side length here is originally 1. So 1 times a half is going to be, is going to be a half. So then I need to draw this line in my scaled down diagram. I need to make it half as big. So it's going to be half of a square instead of a whole square, or half of a side. This guy here in the original is also 1. So I need to make him half as big in this one. So starting here, I'm going to draw a line that's half as big. This side here has a length of 2. So if I'm scaling it to be half as big, it's going to need a length of 1. Now, how do I draw a length of 1 from the middle of this box? Where's the line going to end if I want a 1 unit long box, or side rather, starting in the middle of this box? Yeah, it's going to start in the middle of the box, or it's going to end rather in the middle of the box below. And then this one is the same as that guy there. So this side length of 1 becomes a half of a box. This side length of 1 is a half of a box. This side length of 2 becomes a side length of 1. And then again a half, and then a half, and then 1, and then a half, and a half. So all I've done here now is I've just multiplied each of these sides by the scale factor, and then I drew it the appropriate length. So now what we've got here is a scale diagram where this one is half as big in every respect as the original. Questions, comments, concerns? Okay. Let's do another one. We're going to double it, the letter M. We have a scale factor of 2, and so what this means is that if we have a scale factor of 2, the diagram is going to be twice as big. It's an enlargement of the original. So, and specifically, it's going to be, well, twice as big. We're going to multiply every side here by 2. So let's pick a place to start. I don't particularly care where we start. There are better and worse places to start. Someone tell me where we should start. Carson, you look like you were about to say something. Top right, bold choice. You want me to start right there. Okay? If you want me to start top right, that means my diagram is going to grow to the left, which means I need to put it far enough over to the side so that we have room to grow left. So I'm going to start this thing way over here because I'm not actually sure how much, well, I have an idea how much space we're going to need. So this dot there, our starting point, is going to be this dot here, our starting point. And then Hassan Joe, do you want me to go clockwise or counterclockwise? Okay. So if we're going to go clockwise, this side length here is 1, 2, 3, 4 long in the original. So in our scale diagram, if we've got a scale factor of 2, we're going to take our side length of 4, we're going to multiply it by our scale factor. So 4 times 2 is 8. So this same side in our scale diagram needs to be 8 long instead of 4 long. Starting up here, we're going to go 1, 2, 3, 4, 5, 6, 7, 8. So now I'm down at the end of this side here, so we're going to keep going here. This is 1 long. So I'm going to multiply that by 2, and we're going to have something that's twice as big. This side here goes up 1, 2. So in the diagram, it's going to go up 1, 2, 3, 4. Now the diagonals are always interesting. What is this diagonal doing? It's going diagonal how though, Hassan Joe? Let's connect it to the last unit we looked at. What can you tell me about this diagonal? It has something, starts with an S, has a slope. What's the slope of this thing? Okay, so this thing has a slope, a rise of 2 and a run of 1. So for this guy right here, the slope, if you recall, slope equals rise over run. So in this thing, it's got a rise of 2 and a run of 1. So in our scale diagram, I need to multiply every part of this by 2. Times 2 times 2. And so what that's going to do is it's going to give us a rise of 4. So this thing's going to go back down 1, 2, 3, 4 from this point. 1, 2, 3, 4. And it's going to run 2. So we're going to go down 4 and we're going to go over 2. So that is the new diagonal. This diagonal does the same thing, it just does it the other way. So instead of going over 1 and up 2, we're going to go over 2 and we're going to go up 1, 2, 3, 4. And now we're right here. So instead of going down 2, we're going to go down 4 in our scale diagram. Instead of going over 1, we're going to go over 2. Instead of going up 1, 2, 3, 4, we're going to go up 1, 2, 3, 4, 5, 6, 7, 8. Instead of going over 1, we're going to go over 2. And then these diagonals are the same. This one goes over 1, down 2. So we're going to go over 2, down 1, 2, 3, 4. Connecting those dots. Instead of going over 1 and up 2, we're going to go over 2, up 4. We're going to connect those dots. And finish it off, and now we've got our scale diagram of the letter M. This one is twice as big in every respect as this one is here. All the dimensions are twice as big. We multiplied the original by the scale factor. Comments, questions, concerns? Okay, if there are no questions, then I want you to take a look at pages 4 and 5. There's 4 more there I want you to draw. The scale factors are going to be a little bit interesting. It's the same 2 shapes. I want you to draw this guy here in the letter M. The scale factor is now a 2.5, and this one's now a 3. The scale factor doesn't have to be a nice integer. And then I want you to do question 5 and 6 here too. You've got an arrow. I want you this one scale factor of a half, and this one I want you to have a scale factor of a third. I want you to try and do both of those. I'll walk around and help where needed. On your mark, set, giver. Happy New Year, Miss Craig. How are you? I am not emotionally prepared to be back at work. I got sick on Saturday.
I got sick New Year's Eve.
Yeah. I figured it's better to be sick leaving the break than going into the break.
Yeah.
So, yours was good?
Yeah. How about yours?
Yeah, it was. Yeah, kids had a good time. It was a lot. The beginning was a lot. Like to go from school 3 days, Christmas Eve, Christmas Day. Natasha's birthday is the 26th.
Oh, yeah.
So.
He took off the 20th for a hockey.
Oh, where? Bummer. Okay, you've got your task on your mark, set, go. If you need a calculator to do the math for you, you're welcome to use one. You know where they are. Scale diagram these things. I'll grab some water. Okay, let's do mine. Let's start far enough away to not overlap. And then this guy. Oh. One, two, three, four. Start. So 4 is going to be 2. 2 is going to be 1. 2. 2 is going to be 1. One, two, three, 4, 5, 6. Go with 2. 1, 2, 3, 4, 5, 6. Two is going to be 2/3, 2/3, 2/3. Okay, we done? This one positive thing from the last 2 weeks. One positive thing from the last 2 weeks was the attendance question for today. One positive thing. That's something that gets in.
It was a good time.
Nice.
Very good time. We had a lot of laughing. Something
Nice. Okay, hopefully those diagrams are done. Let's show you what they should look like. Yes, you guys had 15 minutes to draw me 4 pictures. They should be done. Scale factors. Okay, your first two should look like, or first one should look like that. Okay, so that's first one. 2.5 times as big. If you'd like me to go over how I did it, let me know. The 2.5's not bad. 2.5 times 2 is 5, so that one's 5 long. For example, this one's 3 times as big. Scale factor of 3 should look something like this. And again, for these diagonals, you're not just multiplying how long the thing is. You're actually treating the slope. So this guy here has a slope of, it goes over 1 and down 2. So this one, if it's a scale of 3, you're going to go over 1, 2, 3 and down 1, 2, 3, 4, 5, 6. One of the techniques that I saw from, actually it was all named names, Acom. One of the things that Acom did, which is a really a useful way to do this, if you're struggling with drawing straight lines for whatever reason, if drawing is not your gig, I was walking around and I saw he put dots. He started in the top left corner here, and if this is 1, the enlargement needs to be 3, so he went over 1, 2, 3, put a dot. Put a dot, put a dot, put a dot, and just went around the shape, putting the dots out for what the shape, the cage rather, for the shape, and then went back and connected all those dots together. Great way to do that. Especially for some weirder shapes like arrows. For whatever reason, arrows always mess people up. Your arrow should look like this. This little guy is half as big in every respect as this guy is. I know he looks a lot smaller than half as big, but this is what half as big looks like. So this length of 4 became a length of 2. The length of 2 becomes a length of 1. Instead of going over 4 and down 4, we went over 2 and down 2. And then this guy down here, having a scale factor of 1/3 is kind of gross. But if you look at the picture that we had was a big, well, effectively the letter H is just a big square with some bits taken out of it. So I just treated this thing like a big square. It's 6 long this way. So 1/3 of 6 is the same as 6 times 1 over 3, which is the same as 6 over 3, which is 2. So that this side length was just too long. But then to get to this corner over here, I'd recognize that this whole length here is 6. So if I'm going from here to here, 1/3 of that is 2. So I went over 2 full squares and just put this dot in that corner. And then it becomes relatively easy to do. So then I went over 2/3, down 2/3, over 2/3, up 2/3, over 2/3. And I got something that looks like that. So that is what your shape should look like there. There are all sorts of techniques for how you choose to draw these things. Questions, comments, concerns on any of the drawings? If not, then flip the page. The last piece to this is this. Finding the scale factor using the diagrams. So rather than giving you the scale factors and having you draw, I could give you the drawings and ask you to tell me what the scale factors are. So to do that, to find the scale factor, again, it is just what we've looked at before. To find your scale factor, you take a length in the diagram and you divide it by the equivalent length in the original, or the same side in the original. I want to pull my book back up. There we go. And remember, your scale diagram is the new drawing or model. And the original is, well, the original, the thing you started with. And then you just do this division. So if I take a look at what I've got here, the scale factor, I'm going to just show my work here for you for the first couple. The scale factor is going to be equal to, I want the length in the new divided by the length in the same length in the original. So we're going to start up here with a scale diagram, Abdal and Abdul, and we're going to go down. Let's take a look. Actually, it doesn't matter what side we take a look at. Some are easier than others. I would recommend avoiding anything diagonal. So I've got two triangles. I could look at the height or I could look at the base. It doesn't matter. I'll take a look at the height. So this, in the scale diagram, it's 1, 2, 3, 4, 5, 6, 7, 8 long. So that becomes the numerator of our fraction. That's the length in the scale diagram. And now I want to figure out, so this is the side that I looked at. Now I want to figure out how long the equivalent side is in the original diagram. So here I looked at this vertical. So over here, I'm going to look at this vertical here. This guy was 8. This guy is 2. So that's going to be the length I throw down there in the denominator. And now I reduce this. What's 8 divided by 2? So then this thing would have a scale factor of 4. We could do the same thing with the other two sides. We can take a look at the bottom here. This guy down here is 1, 2, 3, 4, 5, 6, 7, 8. This guy down here in the original is also 2. Okay, there's a lot of conversation going on. Abdul. You didn't write down anything I wrote down before, so maybe you should this time. If I take a look at these two sides instead, I'm going to get the equivalent. This guy's 8, this guy's 2, so 8 over 2 equals 4. And there's an extra piece of information here. If you check multiple dimensions and all of them have the same scale factor, this is going to be something that we're going to look at in more depth in a later lesson. If these are the same, if the scale factors for all the sizes are the same, it means that these two shapes are what we call similar. There's a mathematical definition for that word similar, and this is what it is. Okay, so let's take a look at these guys down here. I've got two rectangles. I've got an A rectangle and a B rectangle. A is the original, B is the scale. So what is the scale factor here? Remember that the scale factor, which I'm just going to abbreviate as SF, is going to equal the new, or the diagram or the model, divided by the old or the original. So for this guy down here, the scale factor is, well, it doesn't matter, again, which sides I look at, but they have to be corresponding. So if I look at this left side in B, this guy is 1, 2, 3, 4 long. I have to look at the equivalent side in rectangle A. That's this guy here. This is 2 long. So my scale factor is going to be 4 over 2, which is 2. Equivalently, I could have looked at the bottom of this rectangle. This guy has a length of 1, 2, 3, 4, 5, 6, 7, 8. And this guy down here has a length of 4. So I could have used 8 over 4 instead. And 8 divided by 4 is, again, 2. Scale factor is the same. And then for this last guy here, what's the scale factor to go between the diagram and the original? Which value goes on top? The scale diagram length always goes on top. So they're telling you that this length here in the car is 3 centimeters. And this length in the car is 15 centimeters, and the original is 15. So the original always goes on the bottom. The diagram or the model goes up top. And so then this thing's going to get reduced. 3 over 15 reduces to 1/5. Because both numerator and denominator are divisible by 3. So this is a reduction. But we can find the scale factors the same way. Comments, questions, concerns? Okay, cool. Then I'm done. Your guys' homework is pages 7 and 8. In addition to those 4 drawings if you did not get those things done. There you go. Welcome back.